project presentation. Today we are going to explore how we can use the power of multi-variable calculus, especially Langrange multiplier, to solve a classic real-world optimization problem, which is maximizing land area for a farm. Our project is rooted in a real-world resource allocation problem. Imagine you are a farmer with a fixed budget for fencing, and your dilemma is simple. You want to provide your livestock with the most room possible to graze. However, there is a twist. You are building along a straight river bank. Since the river acts as a natural barrier, you only need to construct 3 sides of the fence. Our goal is to determine the exact dimension, the length and the width that provide the maximum area using your set length of wire. To find this sweet spot, we will apply the method of Langrange multiplier. Let's translate this into math. We have 2 main components. First, our objective function, which is what we want to maximize, area, fxy equal to x times y. Second, we have our constraint. We only have a limited amount of fencing. We let it to be L. Since we have 2 y, we let it to be x, and 1 length, we let it to be y. Our constraint equation is gxy equal to 2x plus y equal to n. Our goal is to maximize f while staying straightly within the limit of g. Now, why do we use Langrange multiplier? Think of it visually. Imagine our area function as a set of level curves that ripples in a point that expands as the area grows. Our constraint, the fencing, is a straight line cutting through those ripples. The sweet spot occurs at the very last moment. The area ripple touch our constraint line. At this exact point, the 2 curves are tangent and their gradient vectors are pointing in the same direction. This is where we introduce lambda. It acts as the mathematical branch that links these 2 gradients together, allowing us to find the absolute maximum area within our limit. It is the perfect balance between our goals and our resources. Now, let's dive into the math. To find our optimal point, we follow a simple 2-step process. In step 1, we find the gradients. The partial derivative of f with respect to s is y, and f with respect to y is x. Doing the same for our constraint function, g with respect to s is 2, and g with respect to y is 1. Moving to step 2, we set up our system of equation. Using the Langrange formula, we get first y equal to 2 lambda and x equal to lambda. And we keep our original constraint to x plus y equal to L. By substituting x and y into the third equation, we find that 2 lambda plus 2 lambda equal to L. This calculation shows us that lambda equal 1/4 of our total fencing, which is the final piece we need to solve the problem.
The next slide is the solution, optimal dimension. So now let's look at the solution for this problem. From our optimization results, we found that the optimal dimensions depends on the total fencing length, which is L, and specifically the width, which is perpendicular to the river, is equal to L over 4, and the length, which is parallel to the river, is equal to L over 2. This means the sides along the river is always twice as long as the sides perpendicular to it. And by using these dimensions, we can also find the maximum possible area. The maximum area is given by L power of 2 over 8. So in general, to maximize the area when only 3 sides are fenced, the sides parallel to the river should always be twice as long as the other 2 sides. And this gives us a simple rule that can be applied to a similar real-world problem. Next, numerical analysis and comparison. So given here, our farmer have a 300 meter of fence, and by using our formula, the sides perpendicular, which is the width to the river, should be 75 meters, and the sides parallel, which is length, should be 150 meters. And for the verification, we take 75 times 2 plus 115 equals to our 300, which is our constraint mass. And for the result, the total area that we got is 11,215 meters square. So next, visualization of the maximum. Okay, so this 3D surface plot helps us to visualize how the area changes when the width and length change. So here, the x-axis represents the width and the y-axis represents the length of the enclosure. And the z-axis represents the area, which is calculated using the formula equals x times y. And the curved surface shows all the possible area values for different combination of width and length. So now, the straight curve here represents the constraint, which is the fencing limit to x plus y equals to 300. This means we can only choose values of x and y that lie along this curve. And the black points here mark the maximum area we can achieve under these constraints. It happens when the width is 75 meters and the length is 150 meters. So this point is the highest point along the constraint curve, which is tells us that this is the optimal design for the enclosure. Okay, so moving on to our final slides, the conclusion and limitation of our project. And to summarize, Langrange multipliers turn a complex constraints into a solvable system of equations. Langrange multipliers provide a systematic method to maximize the enclosure area while satisfying the fencing constraint that will be resulting in an optimal design where the length is twice the width. However, it is important to note a few limitations. And on this project, this model assumes a straight river and a flat land, and it does not consider a real factor such as terrain irregularities or fencing costs. And that concludes our presentation. Thank you.